Now for a little multiplication. We have a special multiplication called dot product. The dot product between two vectors is a real number, not a vector. Important to understand that. It's a special multiplication. It is also known as the inner product. I've never seen a book that uses that name, but I always stick with the dot product. Dot products are used to determine the angle between vectors. Circle this one. That's what we're going to use a lot of. It's used to derive geometric theorems and solve physics problems whenever we're talking about angles. So the dot product of two vectors, let's say u, vector u in component form is a comma b, v is equal to component form c comma d, and we write down u dot v. Now what drives me nuts is that's my favorite multiplication symbol. So now I got to remember that when I put in a dot, it's for the dot product of vectors. So I'm going to have to watch my notations here. We read that as u dot v, and its definition is to multiply the two x or horizontal components, multiply the two vertical or y components, and then add those two products together. And that's what this statement right here states. So to work this out, this component vector 2 comma 3 dotted with the component vector 4 comma negative 1, 2 times 4, 8, 3 times negative 1, negative 3, add them together, 5. It's a real number. If you are over here, looks like I forgot to animate this click, but that's okay, we're here right now. Vector u dot with v, 6 on the I, dotted with negative 2 on the I. That's 6 times a negative 2. 4 on the j times 3 on the j, that will be 4 times 3. So here we have negative 12 plus 12, it's equal to 0. This is a special dot product because if you look at our vectors, we're going to go back to algebra days. This is my change in x, this is my change in y, which means I could write this as the slope of the unit vector 4 over 6, which reduces to 2/3. I do the same thing for the slope of vector v. All right, change in y over change in x. That's 3 over negative 2. So if you look at 2/3 and 3 over negative 2, you should realize, wait a minute, I've seen that when we talked about graphing lines. When I have two slopes that are opposite, positive to negative, and reciprocal, 2/3 to 3/2, these are perpendicular lines. Okay, these will be perpendicular vectors. Anytime you have a dot product that is 0, your two vectors are going to be perpendicular. They will form a 90-degree angle. All right, dot product properties. It's commutative. U dot v is the same as v dot u. If you want to add two vectors together first and then dot it with another vector, it's the same if you take the u dot v, the u dot w, and add those two real numbers together. So if you happen to see two dot products happening and it's the vectors the same, one of them is the same in each one, then it's probably better to factor it out, add these two together, and then dot product. And you can do it in reverse. Add, then dot product. Again, separate. It's just moving this. It's doing the commutative property of this statement. D, if you have a scalar value k being multiplied to a vector u, then dotted with the v, it would probably be smarter to then factor the k out, dot product the u and v together so you're working with smaller numbers, take that answer and multiply it by k. No reason to make these numbers bigger in your vector component form and then do a dot product with bigger numbers. And again, it doesn't matter if k is being a scalar factor to the v or to the u, you can still factor it out in front. The 0 vector dotted with u, well, that in component form is 0, 0, so zeros times these components you'll get 0 plus 0. It's the 0 vector. And anytime you dot product a vector with itself, it's equal to the magnitude squared. And the most important, please highlight this one, put a huge asterisk by it. The dot product is really used to find the angle between two vectors. And it will always be between 0 and 180 degrees inclusively. When you draw a vector, you draw an angle, you always find the angle that's the shortest measurement between the two vectors. So it's always going to be between 0 and 180. And that is to say cosine theta is equal to the dot product of u times v over the magnitude of u times the magnitude of v. Now I'm going to take you back here real quick. What should you do first in that formula right here? You should always do the dot product first. Just kind of crunch it in between your ears real quick, because if your dot product comes out to be a 0, there's no reason to find the magnitude. The magnitude will always be a positive value. You will have 0 over a positive. It's still 0. Once you get a 0 for a dot product, that theta is automatically 90 degrees. All right, example time. Let's find the angle between the two vectors. So again, like I said, mentally between my ears, 3 times 2 is 6, 4 times 1 is 4. Okay, that's not a 0. I need to do the whole thing. Dot product on the top, find the magnitude of the bottom of u and the magnitude of v, and we'll multiply those together. Now, I really contradict the authors on this formula. 3 times 2 is 6, 4 times 1 is 4. That's a 10. 3 squared is 9, plus 4 squared 16, that's the square root of 25. 2 squared is 4, plus 1 squared is 5. In all honesty, I would just leave this as 10. Oh, let me get my iPad here running. Show you what I'm talking about. Okay, where's my notepad? There it is. Come on. Go. Oh, I got something on my iPad. I'm trying to get rid of it, and all I do is move it around the screen. Here we go. Come, no, please, go away. You got to be kidding me. I didn't. Thank you. I tell you, the things I got to do to get this thing to screen share. Sometime today, there we go. Now we're showing up. Okay, clear the page. So, in essence, what I'm saying here is that cosine theta is equal 10 over, when I do these magnitudes, I make one big square root. 3 squared 9 plus 4 squared 16 added together is 25 times. See, I'm already wanting to do my dots. 2 squared 4 plus 1 squared 1, 4 plus 1, 5. Just write it like that. And then do your theta in your calculator and find your inverse cosine of 10 over the square root of 25 times 5. You don't have to crunch it out. You don't have to simplify anything. I don't know why, for the life of me, authors all of a sudden come over here and say, oh, look, the square root of 25 is 5. And then we'll reduce that into 10 and call it 2 over the square root of 5. It doesn't matter. Either way, you are going to get the angle 26.565 degrees rounded to, again, to whatever they ask you to. What I ought to do is I ought to write a college algebra trig book and entitle it Algebra and Trig for Stupid Instructors. Or stupid authors. You do not have to simplify this. Your calculator is going to do the work for the inverse cosine, then just let it here. Don't make any arithmetic errors right here. So there's my angle. And again, this makes sense. Remember, I'm looking at 3, 4. That's a vector, positive, positive in quadrant 1. 2, 1, positive, positive. That's also in quadrant 1. So the angle between those two vectors sitting in quadrant 1 definitely has to be less than 90 degrees. All right, here we go. B, again, if I was doing the work, here's how I would crunch this out. All right, let me clear my screen. Okay, we got 2 times 6 is 12, plus negative 6, doggone it, there I'm doing those dots again, my favorite multiplication symbol. Whoops, that's a negative 12, that's a 0. Don't go any further. Theta is 90 degrees. Don't find the denominator. It is not necessary. Okay? So there's my 12 minus 12 over 0. Now, the only reason I did the denominator is to show one of my properties. Like I said, inverse cosine of 0 is 90 degrees. But let me go back real quick. Back to this property right here. U dot U, that equals the magnitude squared. Okay? So if I come back to here, both of these are going to be, now, I had a negative 6 here, but again, negative 6 squared is just the same as a positive 6 squared. This would be 4 plus 36. This would be the square root of 40. That's this magnitude. Okay, this vector is basically the same numbers, just reversed. That would give me the square root of 40. So the square root of 40 times the square root of 40, square the square root, there's the 40. So it's kind of justifying that one property. That's why I kind of still did that work there. All right. Now, terminology. When vectors are perpendicular, we give them a special name called orthogonal vectors. These are vectors that are perpendicular to each other. Now, why do we add another vocabulary word here? Well, to be perpendicular, that's when your two vectors are perpendicular within the same plane, a two-dimensional plane. We use orthogonal vectors because you may have a vector that's perpendicular to a plane. So that's when you start getting into three-dimensional vectors. You want to have a special name for when you have some geometric shape perpendicular to a plane. Again, to demonstrate that is like take your pencil and have it go perpendicular to your desktop. Your desktop is the two-dimensional plane. Your pencil is the vector being orthogonal to that plane. All right, example 8. A plane with an airspeed of 355 miles per hour is on a bearing of 62 degrees. The wind is blowing from west to east at 28.5 miles. Find the ground speed and actual bearing. Hey, didn't we already do this problem earlier? Yeah, we did. But this time, we're going to work smarter, not harder. We're going to use component vectors. Now, here's my thought. Remember, you're going to find the resultant vector. And we had to do the law of cosines and the law of sines to find sides and angles that were missing in the diagrams before then we did this. Well, now, if you put your two individual vectors, the one for the plane, the one for the wind, in component form, all you got to do is add the x component and the y component, and you have your resultant vector in component form, and we can find the magnitude, and we can find the directional angle, not the bearing, the directional angle, using the a and the b in component form. All right, so let me draw a picture here. All right, so we have a plane, bearing of 62 degrees, so that's north, 62 degrees towards the east. There's my 355 mile per hour vector. And again, because I'm in quadrant 1 here, my directional angle for that vector is 28 degrees. When you want to find the horizontal and vertical component, you need the theta angle from your positive x-axis, your east line, to your vector in a counterclockwise direction. All right, at the tip of this point, it all of a sudden encounters a west to east wind at 28.5 miles per hour. There's that vector. And now my resultant vector is right here. Okay, so vector u plus w. First, find u in component form. Magnitude 355 times the cosine of 28 degrees, not the bearing, the directional angle from the x-axis or the east line. And my vertical component, 355 times the sine of 28 degrees. All right, my wind, magnitude of 28.5 miles per hour, times cosine of 0, and the same 28.5 times sine of 0. No, wait a minute. Cosine of 0, that's a 1. And sine of 0 degrees, that's a 0. That vector's in component form is 28.5 comma 0. U plus v vector is to take the 28.5 and add it to the 355 cosine of 28. There's my horizontal component. My vertical component, 0 plus 355 sine of 28, no change. I found the resultant vector. Now I use the resultant vector to find the magnitude. Okay, everything right here is A. Everything here is B. So to find my magnitude, it's the square root of A squared plus B squared. And to find the directional angle, that'll be from the east line up to the red vector, right there, call that theta, that will be the inverse tangent of B over A. That's these values right here. All right, so I don't want to type these things in twice for these two formulas, so here's my calculator entry. Let's work smarter, not harder. 28.5 plus 355 cosine of 28 degrees. Store it in A. 355 times the sine of 28. Store it in B. Okay, square root of A squared plus B squared. 380.4 miles per hour. Inverse tangent of B over A, 25.98. Well, let's just call that 26 degrees. Now, that's not my bearing, again, and the actual bearing of the plane. So now, what do I got to do? I've got to take this 90 degree from the north, subtract this theta, 26, and that will give you your bearing coming down to the red vector. So your bearing is 64 degrees. Please remember to do that. The number one mistake I find on the test for this is people give me the new directional angle, 26 degrees, and they forget to turn it into a bearing. Okay, and that wraps up our 5.4.